You're listening to Science, Powering Tomorrow, the GNS Science podcast that demystifies complex science concepts and shines a light on its critical and very cool groundbreaking science. Some of my best friends are scientists, and here at GNS, there are endless stories to tell and fascinating people to meet. I'm your host, Dr. Mary Ann Clive, a hazard and risk management scientist with GNS. I am so pleased to have you join me on our storytelling adventures as we dive deep into the science and innovation produced right here at GNS. Together, we'll learn about the critical impact of that cool work and how it is improving our lives and livelihoods every single day. So let's go. It's time to get inspired by science. And today we're talking tsunamis, specifically reducing tsunami uncertainty with Dr. Bill Fry. Welcome, Bill.
Thank you, Mary Ann. Lovely to be here.
As an island nation, we love our coastlines in New Zealand. We live by them, holiday to them, fish from them. But this does not come without its risks. Sitting at the boundary of two tectonic plates and with bragging rights of the 9th longest coastline in the world, we are in constant threat of tsunamis. So can you tell us a little bit about yourself and what you do with tsunamis?
Yeah, I'd be happy to. My formal training is actually in physics. I learned how to study the way waves travel through the earth, the way they travel through the ocean. But now most of my job is really trying to fulfill a passion for reducing disaster from tsunamis. So before the tsunami hits, what can we do to be better prepared for it? As the tsunami is traveling to us, how do we know what the impacts are going to be? And then after the tsunami has hit, how do we improve the recovery of society from it?
And I understand that the RCET program is tackling a lot of these challenges.
Yeah, we're trying, and we've made a lot of progress. We're looking to say as much as we can, as quickly as we can, about the approaching tsunami so we can take the right action before it hits.
So what does RCET stand for?
Rapid characterization of earthquakes and tsunamis.
So it's trying to rapidly figure out what's happening.
Yeah, it's really a change in the way we approach early warning. Before the RCET program, we really viewed early warning as a process of looking at some very simple information we had about an earthquake and trying to put that into the context of what might happen from the tsunami. Now we're trying to understand the physics of what's happened with the earthquake or the physics of what happened with the tsunami generation mechanism, so we can then use sophisticated computational models to provide better understandings about what's going to hit our coasts when it does.
Okay. So just taking a step backwards, can you explain that relationship between earthquakes and tsunamis and why we have so many of them in New Zealand?
Yeah, absolutely. Most of the world's large tsunamis are generated by earthquakes. That's not always the case. Sometimes we have things like the Hungatonga Hunga Hapai volcanic eruption of a couple of years back that generated a tsunami. But for the most part, damaging tsunamis really are generated largely by earthquakes. How that works is that when an earthquake happens, if it's shallow enough and big enough, it can move the seafloor. When the seafloor moves, the water over top of it also moves. And the tsunami is just the physical mechanism by which that disturbance or that movement of the water column goes back to where it wants to be, which is essentially a relatively flat surface constrained by gravity.
And these tsunami waves, they're not the typical sort of big arching wave that you often see depicted in drawings, is it?
Yeah, interestingly, no, they're not. They're really long wavelength or a very, very long wave in the open ocean that when it gets closer and closer to our shores, it gets steeper and steeper. That's typically manifest as a rising wall of water that can flood our coastlines. But interestingly, there were images that came out. One of the first major tsunamis that I was practicing as a duty responder to was the Great Tohoku Oki earthquake of 2011. And in that tsunami, there was video footage coming out from Japan that showed precisely this because of the local bathymetry of a particular part of the coastline. It didn't happen like this all over Japan, but we saw some of those what looked like a gargantuan wave that somehow mimics the type of wave we might see at a normal coast, a normal beach breaking. That's not typically the case, but it does happen, and there's certainly a reason that we see all of that imagery in the old Japanese texts about tsunami.
Interesting. Pretty That was a really extraordinary event, wasn't it? You mentioned being a duty responder. What does a duty responder for tsunamis do at GNS?
At GNS, we have a full system with how we respond to earthquakes and tsunamis, and that goes all the way from people sitting in seats 24/7, looking at continuously streaming data that we have from our observational networks offshore and onshore, all the way through to the bespoke science advice that the tsunami experts might provide for any given situation by analyzing all the available data. So it's really it's a system that involves the rapid first touch of the highly uncertain information all the way through to the very sophisticated modeling and analysis that we get hours into an event.
So sort of a team of scientists just ready to respond and figure out what's happening. Right.
Absolutely a team. Yeah.
Right. So have we had a lot of tsunamis before in New Zealand?
Yeah, we absolutely have. And you mentioned with your preamble about us sitting on top of the plate boundary between the Pacific and Australian plates. Those plates come together at roughly 5 centimeters a year, something like that. That we would call it a convergence, and that convergence generates the earthquakes we see in New Zealand, or a lot of the earthquakes we see in New Zealand. And the fact that we have tsunamis is really responding to that fact. So the more the plates are moving together, the more coastlines you have, then typically the more tsunami hazard you have. In New Zealand, we've had quite a few earthquakes or quite a few tsunamis over the last 100 years that have generated significantly large tsunamis. We had a couple of earthquakes offshore Gisborne in 1947 that generated a 6 and a 10 meter tsunami. We had the 2016 Kaikoura earthquake that generated a land threat tsunami and some damage. That we've had instances like that through time. We know we get tsunamis. We know they're relatively common here, and they're just something we have to deal with.
10 meters. That sounds really, really big.
Yeah, absolutely. We call a tsunami a land threat tsunami if the wave is over 100 centimeters, so 1 meter. So if it's over 1 meter, we say that's a land threat, and that's typically when we issue the science advice that underpins or supports evacuation from tsunamis. So by the time you get up to a few meters, it's quite substantial.
So we know we get tsunamis in New Zealand, and I understand we have a network out in the ocean that it tries to detect them before they hit.
Yeah. For some years now, 4 or 5 years ago, the New Zealand deployed a network of ocean bottom pressure sensors, things that sit on the ocean bottom waiting to feel the effects of a tsunami traveling over it. This is the New Zealand DART network, and it augments a circum-Pacific network of the same type of sensors. What happens is when the tsunami travels over this sensor, it sends a message from a ocean surface mounted or tethered buoy that gives us information in our operational systems very, very quickly with low latency. So we know what the wave is doing offshore before it hits our coast. This is absolutely awesome because before this technology, we were left using information we had that we would call a proxy for the tsunami source, things like earthquake information, magnitude, and a point location to try to understand what that complicated tsunami wave was going to look like. And when I say wave, I mean it's a series of waves. And we were left guessing about what that would look like. Now we can actually measure it as it's headed toward us. And that gives us a lot of information, and it reduces the uncertainty of our forecast by a lot. The DART network is complementary to other information. We don't treat the tsunami as a single data source problem. We believe that multi-data analysis is really the best way to get at a good forecast. For New Zealand, that multi-data analysis is traditional seismic networks, things like the GeoNet seismometer network across the country, things like a global seismic network for that are sensors existing in Pacific Island states across the Southwest Pacific that we use in our analysis. It's things like geodetic measurements from GPS stations that we have real time.
And they measure
ground movement.
Okay.
So the geodetic stations are very good if you're very close to the source. They don't work very well if you're far from the source, and that's one reason they need to be complemented or augmented with other things. Excitingly, we also have a couple of new techniques that are coming online that are just now trickling from the the blue skies research community into the applied research community. I'd like to highlight a couple of these techniques right now.
Yeah.
One is looking at that same geodetic data that we just talked about, the GPS data that measures a location on the Earth. We can actually look at the way the signal from that instrument goes to low Earth orbiting satellites and then is returned. And we can say something about tsunami waves traveling under it. This is because the tsunami traveling in the ocean creates a density change in electrons in the ionosphere. So there are a whole bunch more electrons in the ionosphere that are traveling like a wave through that layer of the Earth, and they're following the tsunami wave. So now we realize we can use these things to extend the look of these instruments, or the distance sensitivity of these instruments, to map the tsunami wave field over distances up to 12 to 1,500 kilometers away from our shores. Another super exciting technique that we're just starting to look into is laser interferometry. What this is trying to analyze differences in light as we send light through fiber optic cables on the seafloor. If there's any sort of movement of that fiber optic cable, we can see changes in the way the light's measured on the other side, or we can send it back to where the light started from, and we can look for changes. What this means is we can likely use fiber optic cables offshore to relatively cheaply monitor whether or not a tsunami's been generated. Right now we have an experiment going on. We're collaborating with the UK National Physics Lab, with the New Zealand MSL Measurements and Standards Lab, and GNS Science, to try to use this technology in the Southwest Pacific on a cable that stretches between New Zealand, Australia, and Fiji, to see what we can actually get out of it and whether or not those data can complement our New Zealand DART network.
So the cable's already out there, providing internet and things, and you can detect changes in that and what's traveling through that cable, and it can tell you about the tsunami.
That's absolutely right. And we do this by putting a very high-powered laser on one side of the cable and measuring the light as it passes through the cable and comes back.
Wow. Are those lasers already there, or is that they're being installed as part of this initiative?
Yeah, in this initiative, we've had a laser for some months now recording earthquakes and tsunamis in the Southwest Pacific. We have good analysis of an event that happened in Vanuatu in December. So we're relatively confident that the method is going to work and it's going to add a lot of information. The beauty of this type of method is you don't have to install the equipment when the cable is installed. We know that the Pacific Ocean has many, many fiber optic cables running through it that have been used, or either currently in use for telecommunications data, or were previously used for things like serving the internet to New Zealand. And we know that you can retrofit this technology to those existing cables, so it opens up a wealth of possibility for future monitoring.
Wow. So you've got, in addition to the DART buoys now, you've got the cables, the laser going through the cables, and also the movements of the Earth and the ions going up to the satellites.
Yeah, that's right. I think right now the promising multi-data really is the early information that we've always had, the seismic type information that we're getting better at looking at, the DART information we have that gives us it's the one thing we can use to give a true, genuine, highly accurate estimate of the height of the wave in the open ocean. The newer techniques, they have promise in that direction, but right now they're providing spatial sensitivity. So they're really good at telling us where the tsunami is or where the tsunami isn't, but they're not very good right now about telling us where what the amplitude or what the height of that tsunami is. So we think by using the gold standard NZ DART network to say something about the amplitude, and then these emergent technologies to say something about the spatial distribution of the wave field, that we're pretty far along the way to forecasting the time dependence or the evolution of the hazard.
All of these tools and techniques help us forecast essentially where and how big the tsunami will be when it reaches New Zealand.
That's exactly right. And we consider the forecasting problem as a life cycle. We know right away when something happens, within the first few minutes of something happening, we have a good idea that a tsunami's been generated. So that's when we typically start our scientific response process. We flip the switch, turn the lights on, we get things going. After we start to get more and more information, this more selective information, we can give forecasts that are accurate enough to base decisions on to say something about the height of the wave when it hits our shores. It's only after the sophisticated modeling, the sophisticated analysis, that we can actually provide forecasts of the evolution of that hazard. So if you think in 4 stages, you might think first is the recognition that something could have happened. The second is forecasting the amplitude. The third is forecasting the evolution. And the fourth is forecasting the cancellation. So when do we think that the waves are going to get small enough that people can safely return to the coast, to those evacuation areas? In the past, if you've lived in New Zealand for the last 2 decades, you'll have remembered times in which we didn't have that information. And it meant that to be safe and to ensure that people had the best chance of not being killed in these tsunamis, we typically were very conservative with the cancellations. So we offered science advice only after we had seen coastal tide gauge stations show that the waves really had subsided. Now we can forecast in advance when that time's going to be.
The tsunami waves can last for quite a long time, can they?
Absolutely. Yeah, for trans-Pacific sources, for tsunamis that are traveling from, say, South America or Alaska or Japan, we might have significant waves in New Zealand we will have well over 24 hours, maybe past 36 or even 48 hours. So they can last a long time. What we typically see is after the significant land threat, I told you land threat was at 100 centimeters, after that goes away, we still have a time where there are unsettled sea conditions, where boaties out in the water need to be vigilant about strange currents or strange sea conditions. And that can last a very, very long time in these big tsunamis.
So the tsunamis can arrive in New Zealand on different time scales as well, depending on where they come from.
Yeah, absolutely. And that creates a particularly challenging problem. If a tsunami originates in South America, for example, we might have 13 hours, 14 hours before any significant waves arrive from that to our coastline. And that gives us a long time to come up with a good forecast based on the data analysis and retrieving all sorts of data. If, on the other hand, the tsunami is locally generated, so if it happens right on our own plate boundary, then we might have much less than an hour time to prepare before the waves hit. This means our forecasts have to be a whole lot faster, and that remains a challenge for future generations of science. So our next big task is to move all of the things that we've done in forecasting the distant tsunamis to the local problem.
Yeah, under an hour is not a lot of time to turn all the lights on, get the science sorted, and then get our communities ready, is it?
Yeah, and if you think about that in terms of the whole chain, the warning chain, you have to think about the data getting to us, about our analysis of the data, the forecasting, and then the emergency response part of the chain, getting that information to the potentially affected people and getting the action taken that we need to keep people safe.
And that action that we need to keep people safe is?
Evacuating the coast when there's a land threat, getting people out of harm's way.
I suppose the long, strong, get gone becomes really useful in those local contexts.
Absolutely, it's useful. But we need to remember also that a local earthquake and a local tsunami source, say, for example, that hits the central North Island, might be a regional source for people in the South Island. So for people in Littleton, you might have a couple of hours before the significant waves hit. So even those local earthquakes, even with long or strong get gone, we also need to do all we can to understand the evolution of the hazard and recognize that there will be places on the New Zealand shores where we won't get that natural warning. So the real challenge now is understanding how best to complement natural warning with our scientific approaches.
Right. I have something here about digital twins, I'm curious, what do digital twins mean in the context of tsunami forecasts?
Yeah, great question. A digital twin is really a way that we can use high-performance computing, modern computational approaches to model a system and understand how the system might change or might evolve given different circumstances. It's really the next big thing in our systemic tsunami preparation and response. If we can use the physics we understand about the tsunami process, the multi-data that we've talked about, and also an understanding of the evolving exposure or the evolving situation of a developing geohazard in New Zealand, we can throw all these things into the mix and try to understand from a computational perspective how that system might evolve. For example, imagine a future in which we could generate a sophisticated tsunami model. We understood how the tsunami was going to impact our coastline. And imagine at the same time, we had an understanding about the dominant evacuation routes in our coastal cities. Well, there might also be other things affecting this, like, for example, construction on a bridge that might limit the ability of people to evacuate over that bridge, or obstacles or hazards that might be generated by the tsunami source process, like strong shaking from a local earthquake and liquefaction. What a digital twin would allow us to do is to understand in real time and in time to affect our emergency response what the likelihood, say, for example, of people being trapped in a particular place might be, or where the most effort needed to be to help with the response or the emergency management.
Wow, that sounds really useful. And that would capture factors in the hazard, but as well as factors in the people and the environment that they're having to move in and how that might change.
It treats the hazard as a system rather than what we commonly do now, which is focus on an individual peril. We might try to forecast a tsunami wave, or we might try to explain where the strong ground shaking has been from an earthquake, or being a decision maker and responding to a big tsunami, we might try to figure out what's the best way to get the most people out of harm's way. The digital twin paradigm allows us to put everything together, to smash it up, and to see how those have dependencies on each other, to see how the system works. So it's not just people in isolation, it's not just the hazard in isolation, it's both together. And what are those effects? And how can we use an understanding of that to make New Zealand as safe and resilient as possible?
Yeah, so I understand in one of the more recent threats that we had from the Hongatonga eruption, that was concurrent with a cyclone. And so that added that complication of having the hazard occur in another context.
We know when we get these cyclones or extratropical cyclones, we might get storm surges that are significant hazards in and of themselves. And we've got systems to forecast that type of hazard. We've got systems to forecast the tsunami hazard. Exactly as you say, when you put the two together, it might be a totally different hazard on our coastline. There are also situations like the Kaikoura earthquake. The Kaikoura earthquake generated a significant land threat tsunami, so a tsunami over 1 meter high. And it also happened at a time at which the coastline was actually uplifted in central Kaikoura. So when you add the tsunami and the coastline, then you get offsetting effects. Then if you add the tides in, which the largest waves really happened at a low tide, it gives you a more significant buffer against that land flooding. So we need to factor in all of these things, especially for our closest sources, for our local sources.
Oh, wow. Yeah, there's a lot at play there influencing that. One of the other recent events that happened in New Zealand was I think it was called the Tsunami. Can you explain what happened on the Tsunami day?
Yeah, absolutely. Within a 12-hour window, we had a couple of magnitude 7+ earthquakes that happened just offshore off of the Rakumura Peninsula. And we also had a Kermadec, a central Kermadec earthquake. When we talk about the Kermadec, we're talking about this plate boundary that stretches north of New Zealand up past Raoul Island. In that morning, the Tsunami day, we had 2 magnitude 7+ earthquakes offshore Rakumura, and we had an 8.1 earthquake that happened up in the Kermadec. It meant that our response processes, our tsunami expert panel, we were trying to still deal with the yearly event when the middle event was the 8.1 in the Kermadec. When it happened, it meant we had to consider the fact that some of New Zealand's harbors, they trap energy. What happens when a tsunami comes into a harbor, quite commonly the harbor can hold that energy, and it it manifests as a wave bouncing back and forth in the harbor for some time. And then if you add even more tsunami to that, the interplay of those waves makes our modeling a lot less certain. So on that day, we were still dealing with the uncertainty around the early magnitude 7 event when the magnitude 8 event happened. So we were trying to understand what that meant, how the two were going to work together to generate tsunami hazard, especially for our harbors.
I suppose the threat can last longer in the harbors potentially then because of that trapping of energy.
Yeah, and that's also why we commonly see that the first wave is the largest wave of tsunamis. If you're, for example, sitting in the Wellington Harbor, in most of our simulations and events we've seen, the largest wave might be the 6th or 7th wave. You might not get the largest waves coming in until 5 hours after the first wave hits the Wellington coastline.
So that concept of forecasting the wave over time becomes, I guess, quite useful.
Yeah, not only useful to keep people out of harm's way, but also useful for infrastructure providers, for harbor masters, or people that are trying to understand the implications of the tsunami on other things other than people sitting at the coast. That time-dependent information is tremendously valuable to make decisions about when ports can reopen, when transportation lines will be accessible again, when can you start using the state highway in Wellington to bring emergency response supplies or use it as an emergency pathway.
And some of these new tools through RCET are helping us understand that time dimension.
The biggest challenge with forecasting the evolution of the tsunami previously was that we were using earthquake proxy information. We were using some very simple information about an earthquake source to generate our forecast. This meant the uncertainties in our forecast were much too large to provide useful information in most cases about the tsunami evolution. Because now we can base our forecasts on ocean observations, on direct observations of the tsunami rather than on the proxy earthquake source. So in the presence of the New Zealand DART network, we can now do that. We can now look at the tsunami wave traveling toward us. We can use that to make a forecast, and the uncertainty is reduced by doing that because we're looking at the actual tsunami wave. We can reduce the uncertainty to the point that we can now say useful things about the evolution of it and the time dependence of the hazard.
So it sounds like there's been a lot of really exciting things happening in the tsunami response toolkit space. What's next?
Next is really a multi-data digital twin.
Right.
So next is trying to use all the available data we have and all the available data that we might be able to assemble to forecast this process and the impact of this process. So what is the tsunami going to do when it hits us, and how can we make decisions in real time that will support the response and recovery?
It sounds like really useful science for New Zealanders, and really exciting stuff. And it makes me think about how you got into this field. What attracted you to tsunamis and led you to do work in this space?
Yeah, interesting question. As I said in the introduction, my background is in physics, and the way we can go from a whole lot of data in a complicated solving of a lot of equations at the same time to a source and how that affects the way energy travels through the Earth. At some point in time, I took a step back and I said, why are you doing this? What do you want to get out of it? And that happened just about the same time that I'd moved to New Zealand in 2008. And we had the 2009 Dusky Sound earthquake and tsunami. I was a duty seismologist at the time, a duty officer, and I can remember responding to that event. And I can remember not having much information to communicate to the decision makers because we didn't have the ability to provide the science advice in real time. And that was really a transition for me because I understood there was a lot that we were doing in theoretical space, a lot we were doing in academic space that really needed to be provided in real time. That stuff that we were doing, the months to years after a big earthquake or a big tsunami happened, if we could do it right away in real time, then we could improve that response. We could provide people with more science information. So that really drove me to where I am today, trying to make sure that we take the most cutting edge physics we can, the best globally leading science we can, and smash it into the response system.
No small task.
No, but we have a wonderful team in New Zealand. Of course, we have a lot of the world's geohazards here. Well, we also have a lot of the world's capability in geohazard science, and I'm fully confident that with this world-leading team, we can make advances.
Well, that's fantastic, Bill. Thank you so much for coming and chatting with me today about tsunamis and how we're using all these different techniques to reduce the uncertainty and better understand what's going to happen and how we can keep people safe when it does.
Thank you, Marianne.
And thank you, listeners, for tuning in. Today's discussion is just the start. We have so many cool stories to tell here at GNS Science, so be sure to check back in on our podcasts. We are going to be delving deep into our natural hazards, our future energy solutions, the wonders of our environment, and the climate challenges we face. We'll be taking a look at the clever ways we dig deep and learn about New Zealand's past, and how that helps us forecast our future. Don't forget that you can keep up to date with all things GNS at gns.cri.nz or on all our social media channels. Join us in the next Science Powering Tomorrow episode. Thanks for listening.